So here we are picking up with number 6 on the Particulate Modeling for Limiting Reactants practice sheet. In this reaction, chlorine gas will react with fluorine gas to produce chlorine pentafluoride gas, and it tells us to write the balanced chemical equation. So this is kind of review. Chlorine, I know, is a diatomic, so I'll put Cl2. And fluorine is also a diatomic, so F2 gives us chlorine pentafluoride. So that would mean there's 1 chlorine and then 5 fluorines, pentafluoride. Now this is clearly unbalanced, so I'm going to put coefficients to balance my chemical equation here. I have 5 fluorines on the product side and only 2 on the reactant side, so I'm going to need to get to an even number of fluorines. So I'm actually going to skip fluorine and start with chlorine. I notice I have 2 chlorines on my reactant side and only 1 on the product side, so I'm going to go ahead and put a 2 in front of ClF5, which then gives me an even number of fluorines. So 2 times 5 gives me 10, so 2 times 5 gives me 10 on my reactant side as well. So sometimes it's best when balancing doesn't seem to be working out to just start with the other element. So there's our balanced chemical equation. Problem 1 says if we have 2 moles of chlorine and 12 moles of fluorine gas, how many moles of chlorine pentafluoride will be produced? And it asks us to draw a picture or a particulate model of this scenario and specifies that we should draw the exact correct number of each type of atom or molecule. So we'll start by just simply drawing this scenario at hand. So let's see, 2 moles of chlorine gas, and so chlorine is a diatomic, so I'm actually going to change this here. It has the chlorines as white, so chlorine, 2 diatomic chlorine, 2 moles of that. There we go, we drew our chlorine, and then 12 moles of fluorine gas. So 12 diatomic fluorines, and it tells us to make our fluorine black. So color those in. So 1, 2, 3, 4, 5, 6, 7, 8, 9, I'm running out of the room here, 10, let's see, I can fit one down here, 11, and 12. 12 separate molecules of fluorine gas, and I know that I didn't quite color some of these in, so just bear with me. Do the best you can on the coloring there. I just wanted to make sure it's clear which ones are the fluorines and which ones are the chlorines. And so to figure out how much chlorine pentafluoride is produced, I need to figure out how many times this reaction can happen. So what I like to do is just kind of circle the reactants needed for each time we do this chemical reaction. So for each time we do our recipe, we're going to need to use 1 Cl2 and 5 F2s. And out of that, we'll get 2 ClF5s. So use 1 of Cl2, and then 1, 2, 3, 4, 5 F2s. So there we go, we're doing our reaction once. These are all the ingredients needed to complete our reaction one time. And then let's see if we have enough to do it again. It looks like we do. So I'll do the reaction again. So we still need 1 Cl2. And I'll actually do this one in a different color. 1 Cl2 reacting with 5 F2s. 1, 2, 3, 4, 5. So there we can do the reaction again. This is the second time we're doing a reaction. And then we can't do the reaction a third time because all we have left is fluorine now. We're actually out of our Cl2 molecules. We have no more of our Cl2 reactant. And so in this scenario, the Cl2 is our limiting reactant, and we have an excess of fluorine, of F2, of fluorine gas. And so I'm going to go ahead and start by transferring my excess reactant into my products picture or my post-reaction picture, because I know that the excess doesn't go away. So this right here would be my excess And so this doesn't go away. It's still present after the reaction is finished. So I'm going to go ahead and draw these on my product side. So there is my excess fluorine, and now I just need to figure out how many ClF5s are produced. Well, since I was able to do the reaction twice, I'm going to essentially do my recipe, which is shown up here 2 times. So if I go through this process twice and I use 1 chlorine and 5 fluorines to produce 2 ClF5s, every time we do that we get 2 of our ClF5. So since I did this twice, I'm going to get twice that many. So 2 ClF5s, and we were able to do this twice, so we're going to end up with a total of 4 ClF5 molecules. So I just need to draw those on the product side, those 4 ClF5s. So I'm going to start out by drawing my Cl's in the middle, and then 5 fluorines on the outside. 1, 2, 3, 4, 5. Not a perfect picture. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. So it's not a perfect, great, wonderful, beautiful drawing, but it does get across the idea as to what's happening in this chemical reaction. So we go from our reactants on this side, unreacted, to our products, and then our leftover or our excess reactant. So there's my diagram. So we also can determine the result of a non-ideal stoichiometry problem, so a limiting reactant problem, mathematically, and that's what we're looking at next. So we're going to start out by filling in our reaction table, and we've actually already written the reaction on the previous slide, so you can just kind of rewrite the balanced reaction in the table here. So Cl2 plus 5F2 gives us 2 ClF5, and it is the same reaction, but we're also going to add up the molar mass of each of these substances. So for Cl2, I'll take that 35.45 and times 2, multiply by 2, to get 70.9 grams per mole. For F2, 19 times 2 gives me 38 grams per mole. And then ClF5, if I add all that up, 19 times 5 plus 35.45, I get 130.45 grams per mole. So now I have all our molar masses calculated for later in case we need them. And this time we want to actually calculate, using dimensional analysis, how much ClF5, and it specifies in moles, can we make with each of our reactants. This is the same amount of reactants that we drew our picture of above, the 2 moles of Cl2 and 12 moles of F2. So basically we're just going to do our dimensional analysis twice and figure out which one of our reactants produces less product, because whichever one of our reactants produces less product is going to stop our reaction occurring. Once the limiting reactant's used up, we have to stop doing the reaction. And so we're going to start with 2 moles of Cl2 and 12 moles of F2. And we're going to use a little bit of stoichiometry to convert both of these into moles of product, or moles of ClF5. So I'm kind of doing these in tandem here, but you don't have to do them that way. You can do them one at a time. So in this first one, my moles of Cl2 goes on bottom, and we're trying to go to moles of product, ClF5. And then on the second one, where moles of F2 needs to cancel, but once again we're trying to convert to moles of ClF5. So by converting both of these into the same substance and unit, I'll then be able to compare how much can be produced by 2 moles of chlorine and how much can be produced by 12 moles of fluorine. So we just need our mole-to-mole ratios here, and we'll look at our balanced equation. So for every 1 chlorine, we're going to end up with 2 ClF5s. And for every 5 fluorines, we're going to end up with 2 ClF5s. So this is just a matter of multiplying and dividing. So 2 times 2 divided by 1 gives us 4 moles of ClF5. And then 12 times 2 divided by 5 is going to give us about 4.8 moles of ClF5. Okay, so our fluorine, or 12 moles of fluorine, could have produced 4.8 moles of ClF5, but before we were able to use up all of our fluorine, we actually ran out of chlorine earlier. We only were able to produce 4 moles of ClF5 with that 2 moles of chlorine. And so our chlorine is our limiting reactant because it produces less product. So our chlorine here is our limiting reactant. And therefore our theoretical yield, or the amount that we'll actually be able to produce, is the smaller number, the 4 moles of ClF5. We're not going to be able to make 4.8 moles because we ran out of Cl2 gas. So the limiting reactant in this chemical change is the Cl2. It is not 4 moles of ClF5. That's the amount of product that's produced. So another way of saying that is this is our theoretical yield. But a lot of the times when students are rushing, what tends to happen is you just take your answer and substitute it in as the answer for the limiting reactant, when in fact ClF5 is not a reactant at all. Our limiting reactant is Cl2 in this case. It's the thing that we started our stoichiometry with. And then how do we know that this was the limiting reactant based on our calculations? This is simply because it yielded less product. So you're looking for the one that has the lower amount of product. And then what is the excess reactant in this chemical change? Well, that would be our F2. This is available in excess. There's going to be an excess of F2. So F2 is our excess in this case. So in this next part of the problem, in problem 2, it says how many grams of chlorine pentafluoride gas can be produced if you have 80 grams of chlorine gas and 40 grams of fluorine gas. And so in order to do this, we're going to do this almost the same way, but this time we're given grams, so we're first going to have to convert our grams to moles, and then use our mole-to-mole ratio to figure out how much ClF5 can be produced. And then once we figure out my moles, you could go all the way to grams and figure out which reactant produces fewer grams, but what I like to do is take them both to moles, compare the number of moles that can be produced, and then only convert the actual theoretical yield to grams. And so that's what I'm going to do here. And so Cl2, if Cl2 is limiting, I'll start with 80 grams of Cl2, so I'll start there. And I'm first going to go grams of Cl2 to moles of Cl2. 1 mole I have in my table equals 70.9 grams. Nice that we already filled that information in. Then we will go from moles of Cl2 to moles of ClF5. Okay, and then for F2, we would start with the 40 grams of F2. And then we'll put grams of F2 on bottom, and then moles of F2 on top. And we know that 1 mole of F2 equals 38 grams. And then we will go from moles of F2 into moles of our new substance, which once again is ClF5. This way we'll be able to compare our amounts. So in our chemical reaction, there's 2 moles of ClF5, so I can put that on top of both of my mole-to-mole ratios. And then Cl2, there's just 1 mole of Cl2, and F2, there are 5 moles of F2. And so we'll do this dimensional analysis and figure out our answers here. So let's see. 80 divided by 70.9 times 2 gives us 2.257 moles of ClF5. And then we will have to do F2 as well, so 40 divided by 38 times 2 divided by 5 gives me 0.42105 moles of ClF5. Okay, and so clearly our fluorine produced far less product than our chlorine did, and so our limiting reactant must be our fluorine. So I'm going to go ahead and label that. So here, fluorine is our limiting reactant, which means that this right here is our theoretical yield. So I'm just going to put a little X through this so we know not to use this. We're not going to get that much ClF5. We're only going to get 0.42105 moles. And this is actually asking for how many grams of chlorine pentafluoride can be produced. So I'm going to have to take this moles that I've gotten and convert this to grams. So we'll just put moles of ClF5 on bottom, and then grams of ClF5 on top. And I know 1 mole of ClF5 is 130.45 grams. And so when I multiply that out, I got 54.9. But of course, in our problem, we're actually only given one significant figure, which is somewhat problematic. I'm actually thinking that maybe there's a typo here and it's supposed to be 2 significant figures, but since it is only one significant figure, we will round to just 50 grams of ClF5, because that's the best we can do here with just one sig fig. And then on the next page, it says, what is the limiting reactant in this chemical change? So if we go back and take a look, our limiting reactant was F2. It's nice to have all these things labeled so we don't get them mixed up. What is the excess reactant in this chemical change? Well, that's the other one. That would be the chlorine, the Cl2. There's definitely excess Cl2. And then it asks us how much of the reactant available in excess was actually used up. And it gives us the hint, convert the amount of limiting reactant to the stoichiometrically equivalent amount of excess reactant. So we're going to go back and look, and our limiting reactant was F2. So we could start with 40 grams of F2 and convert that back to how much Cl2 we need to use. But I also know that it would be easier to go straight from moles to moles of another thing. And I know that 0.42105 moles of ClF5 is stoichiometrically equivalent to 40 grams of F2. So I'm going to actually start my dimensional analysis with the 0.42105 moles of ClF5, 0.42105, 0.42105. And this is in moles of ClF5. So I just want to convert that to my grams of my excess reactant, grams of Cl2, but I can't go straight from moles of one thing to grams of another. I first have to go mole to mole. And then I can take my moles of Cl2 into grams of Cl2. And I, of course, have those values from before. So I know that based on my table that I've already filled in, ClF5, 2 moles of ClF5 are stoichiometrically equivalent to 1 Cl2, and that 1 mole of Cl2 is equal to 70.9 grams of Cl2. And so notice this is just a whole lot of work here, but it's not really that difficult, it's just a lot of steps. So when I multiply this out, I got 14.9 grams of Cl2. And remember, this is the amount of Cl2 that was used up. So to figure out the remaining amount of Cl2, all I have to do is take my original amount, so 80 grams of Cl2, and subtract out the amount that was used. So that's my last step here, 80 grams of Cl2 minus the 14.9 grams that are actually used. So 80 minus 14.9 gives me 65.1. But of course, when we do subtraction for sig figs, we're looking at decimal places, and 80 doesn't have any decimal places, so we're also going to round our answer to a whole number. So 65 grams of Cl2 remain. And there you have it.